Welcome back to the second lesson of week 2. Last lesson you learned about fixed point numbers, and this lesson we're going to look at an alternative, which is the floating point number. And once again I've chosen a picture that I like, which is vaguely related to the topic because it shows two fixed boats that are floating, but that's really got nothing to do with the topic. I just like the picture. So in this lesson we're going to recap what we know about binary position values and fixed point numbers. We're going to think about how range and precision can be traded off and how a floating point number offers a solution to this problem. So to recap, binary integers are made of a series of 8 binary digits, bits, and the position values are powers of 2, and the range is from 0 to 255. So what's that number? How would we work that out? We would add up the values of all the positions where there's a 1, so 64 plus 32 plus 4 makes 100 in decimal. Fixed point numbers work in exactly the same way, but the values to the right of the point are fractional values, and therefore we can be more precise. We can go down to values that are less than 1, but we have a smaller range of numbers. We can't go up into the 200s. What's this number? Well, it's 8 plus 4 plus 0.5, so it's 12.5. In fixed point binary, those positions are set in advance, and all the numbers that are stored in that block of memory have the same column values. And if you want to add a number, or let's say after an addition you've created a new number, whatever number you've got, it's got to fit in to those position values. They can't be adjusted. So I'm going to give you the answer to this on the next screen, but what are the disadvantages of storing numbers in that way? So the computer has decided the column values in advance, and every number must fit into that position grid. And some numbers might require a greater range. They're bigger than that, and so you get the problem of overflow. And other numbers might require additional precision, so they're very small fractions, and that would be truncated or rounded because we can't get more precise. So the solution to this dilemma is to use floating point numbers. That's a different way of storing fractions. In every number, the binary point is put into a different position, and the computer works out the best place for the point in order to get the maximum range and the maximum precision for each number. A floating point number is stored as 2 numbers in the computer's memory. They're called the mantissa and the exponent or exponent. The mantissa is a pattern of 1s and 0s, so it's recording the pattern of 1s and 0s that makes the binary number. And the exponent is a power of 2 that shifts the binary point up and down the byte to left or right to put it into the best position. So if we compare those two methods, fixed point numbers don't take up as much space because they're only stored as a single number, and they're quicker for the computer to process because it doesn't have to do any working out. But the disadvantage is that it's inflexible, so you're more likely to get overflow or underflow, lose fractional values and so on. Floating point is better in its precision. It works out the best possible way to store the number to get the precision that you need. The disadvantage is it takes additional storage space, but most importantly, it takes an additional processing step because the computer has to work out the number from the stored mantissa and exponent. So you can imagine if you were building a computer that had to deal with split-second crises, let's say it's landing a plane, you might think that the precision of a fraction of a millimeter here or there isn't as important as lightning speed of calculating the right thing to do. So you might use fixed point numbers. But in general, we tend to use floating point, and as you know, Python uses floating point numbers. So let's recap what we've learned in this lesson. We've learned how fixed point numbers work, and we've learned in principle how floating point work by storing a mantissa and an exponent. And we've looked at the advantages of the two methods. You might be thinking, I don't yet know how to make floating point numbers in detail. Don't worry, that's next lesson. So I'm leaving you with this list of key terms. Make sure that you've got revision notes on the meaning of each one of these terms, and go on to the next lesson to learn how to make floating point numbers.